Swayam Prabha. Digital India. Educated India.
So, in the last class we looked at the scope of deterministic modeling approach. So, this deterministic approach allows us to model a physical, chemical, biological phenomena by following certain conservation laws, constitutive relations, symmetry laws, and then give a quantitative mathematical expression, and then you can solve them analytically or numerically to get an answer, and this answer is a certain answer. Okay, you get a single outcome. So, that is the nature of a deterministic modeling approach. Now, there are other scenarios where such single outcome response is not always the case. Okay. Sometimes we see some phenomena where the outcome or the response seems to be of multiple possibilities. Okay. So, we wanted to kind of develop some mathematical tool to address such phenomena. Okay. So, I can give two examples. So, irregular dynamics. Okay. So, that is what we say as a stochastic or random process, and I want to give an example of this, maybe two examples. One is a Brownian particle or Brownian motion. This is something that one can easily do an experiment and study a Brownian motion. What it means is you take a simple liquid like water, and then you disperse a particle that are micron and below size, and then if you see this particle's trajectory or coordinates positions in a microscope, you will see that the dynamics of this particle is quite irregular. Okay. So, pictorially you can think of, in a two-dimensional representation, you have this particle. So, we say that the size is of the order of 1 micrometer. Okay. It could be anything, it could be a pollen grain, it could be a solid particle, it could be a cell, biological cell, it could be any object, soft or hard, could be made up of any composition, but as long as they feature in this particular size, this phenomena that I am talking about, the irregular motion is present. Okay. So, what happens is that this is suspended in a continuum of solvent, and if I denote the solvent molecules as these points, and at finite temperature these molecules have kinetic energy. So, they move about, and when they move about they also encounter collision with this particular object. Okay. You can see I have deliberately made the size difference between the particle and the solvent molecule. So, the size difference is very large. The object is much larger, 3-4 orders of magnitude larger than the size of a solvent molecule. As consequence of that is that the dynamics of these molecules are very fast compared to the dynamics of this particle. Okay. So, if you look at a time scale, the time scale with which these molecules relax is very short compared to the time scale with which this particle relaxes. Okay. That consequence comes because of the size and dynamics. Now, what happens is that at any given moment of time, there are millions and trillions of molecules are actually hitting this particle all around it. Okay. So, now this particle will have to respond in net effect to all these collisions. Okay. So, now if our observation is over a period of time where I am looking at a time scale where the molecules of water relax very fast, but I can capture the dynamics of this particle. In that particular time scale, you will see this motion of this particle is irregular. It jumps somewhere here, comes here, goes here. So, you will see that some sort of irregular behavior. Okay. So, I might have started here at time t equal to 0, and then over an observation time delta t, I would see this particle moving somewhere here. okay, the other sampling time interval, it would have moved here. And then if you follow the time trajectory, you would have probably ended up somewhere here at time t. And if you make a fresh observation from this point, you would exactly create another similar set of irregular motion. Okay, and this motion is very different from a projectile motion or a trajectory of a rocket or a ball that you throw. Okay, this dynamics is very different. So now the reason why this exhibits such a way is because we are looking at the dynamics of one particle whose dynamics is affected by an incessant collision of many independent collision of many solvent molecules. Okay, so this is one scenario where the stochastic exhibition, the irregular motion, comes about whenever you look at an observation where the dynamics of this particle is influenced by a sum or net effect of many independent events. Okay, and that was going to give rise to this kind of Brownian motion. Okay, this is one scenario. I can give another scenario in polymer dynamics. Very simple polymer like polyethylene has a structure which has a repeating unit of ethylene unit. So it goes on like this. Okay. Now you can also represent this as a simply CH2CH2. Okay, n repeating. So I am taking one ethylene molecule and I am just stitching it along with in a linear way. So I get a very long high molecular weight polymer. This is atomistic level or chemical detail. But if you want to come with a mechanical model for this polymer, generally you try to say one monomer unit connected to another monomer unit in a bead spring model. Okay, this is like more like a mechanistic model for the polymer. Okay, so this is called bead rod or bead spring. These are different ways to represent the chemical details into a simple artistic representation. Okay, so we say that each monomer is connected by a bond, and you can have as many number of bonds as you want. Okay. So now if you look at, now the question we want to ask is, what would be the end-to-end distance of this polymer? I put this polymer in a solvent, and this molecule is not going to be stretched out like this. It's going to take a different conformation because it likes a solvent, it is very dynamic, okay? It undergoes a lot of dynamical motion, and the question we are asking is, what would be the end-to-end, suppose I have a very long chain, these are my end groups, we are asking what is the end-to-end distance vector and what is the distribution of that. So suppose if that is your observation that you can make, you want to understand, then this end-to-end distance is actually determined by sum of the individual displacement of each one of them, right? Suppose I start from here. Now this second node or the second bead can be anywhere in a radius of the bond distance. Okay, so let's say at one moment it is actually somewhere here. The one that is connected to this also has another possibility of to be found anywhere in this circle. So let's say it comes here, and then I can keep on building this. So we can see with respect to this particle can be anywhere in this particular circle. I am talking about circle in 2 dimensions, but it's going to be a sphere in a 3-dimensional space. Once this position is obtained, then this molecule can relax to find its own place. And then you see that when you have this number of repeating units of the order of hundreds and thousands, you can see how many independent ways each of these monomer can actually take position. And once you execute this, the final, so this is going to be extended, and the final one probably can be somewhere here, we don't know, okay, because there are so many possibilities. Now we are asking what is the end-to-end distance vector r, and what is the distribution of that? Okay, is it going to be a certain value or is it going to be a random variable? That's the question we are asking. Suppose if this polymer does not make any flexibility, if it's a rod like, then you know that the end-to-end distance is nothing but the total length of the polymer. Okay, that is a deterministic variable. But as I said, this polymer is very dynamic. Once you put it in solvent, it is going to undergo a lot of this, because it's interacting with the solvent, there's a kinetic energy, there's a temperature. Because of that, this monomer is going to move about. So you're going to execute this kind of motion, and then you have multiple outcomes for the end-to-end distance. You can actually work this out theoretically, and what you will see actually is the probability of finding this end-to-end distance vector is actually a Gaussian, centered at 0. Okay, and the standard deviation of this distribution is going to depend on the chain length. Okay, so the point I'm trying to make here is that this problem and in this problem, in both cases, the observation that we want to make is being affected by many independent random variables. In this case, the multitude of collision of the solvent molecule to the particle gives a net effect to the particle. Okay, the dynamics of this particle is going to be influenced by this net effect. Okay, and then it shows this kind of irregular motion. Similarly, in this case, when you have a long chain polymer molecule where each segment has a particular way of moving about and each of them can do independently, okay, the motion of this is independent of this one. Okay, so then the end-to-end distance vector that you want to find out is a collective effect of all these independent random variables. Okay, then experimentally or by theoretically, when you look at the distribution, you will see it forms a nice Gaussian distribution. In fact, the same thing can be said about this particle also. Okay, so if you look at the particle position, Brownian particle position, that would also have a distribution according to a normal distribution. Okay, so the width of this distribution is going to be proportional to the temperature, the size, how big the particle size, and so on. And what's the temperature, what's the viscosity, those are the effects. Okay, so even though in these two problems we show normal distribution, it is not that all random processes and stochastic processes will follow normal distribution. There are other kinds of distribution also. So that is the context we are trying to say. So now we can give more such examples, but the point I'm trying to make here is that in this particular conditions, there is a way that you can look at the problem from a stochastic point of view or a probabilistic point of view rather than in a deterministic point of view. Okay, and we make that statement because there is a particular time scale we are looking at these objects and we make these observations. Okay, so now the rest of the course is going to be looking at various theoretical framework for understanding these kind of processes, but before we go there, I wanted to give some elementary introduction to probabilities and probability theory so that we are on the same page. The material I'm going to cover is something that you already studied even in schools, okay, but still for the purpose of this course, I think I want to kind of take it as a review, okay, or revision, and it may be boring for some of you, but it may be useful for some others. Any questions on this discussion so far? So what I showed here is a Gaussian chain, but if you want to include those interacting real chains, we can do that also. Yeah, yeah. So here I have assumed them to be like an ideal chain, but I don't want to give too many technical term here. This is something we will do it later. Okay, it is not just introduction, but it's an elementary introduction. Okay, so that means we are going to go to very basics. We say that a random variable, in short I use RV, okay, or a stochastic variable X. Okay, so this is defined by two things. One is it is defined over a set of possible values. So we already introduced the probabilistic characters to this variable X. Okay, X can take a set of well-defined set of variables. Okay, and the second is that it has a probability distribution over this state. So when we try to define a random variable, we need two things. One is we want to say what are the set of possible values it can take, and the second is these variables are taken by an underlying distribution. Okay, each of these values may not be equally likely. Some values are more likely than the other. Okay, and that information is given by the probability distribution. Okay. Now when we say this set can be, it can be a discrete set or it can be a continuous set. So when we say discrete, we mean that let's say if you want to look at the number of molecules in a reacting mixture, okay, so that is an integer variable, so that's a discrete number. Okay, so number of molecules in a reacting mixture or number of electrons in a conduction band. I don't want to give the typical example of a head or tail or a number of outcomes of throwing a die. Those are very trivial examples, but these are examples that more relevant to engineering applications. Okay, so you can see these are all individual variables. Number of electrons in a conduction band or the number of molecules in a reacting mixture. These are all integer variable, and it has a particular range of values it can take. Sometimes it can be a continuous. An example could be the velocity of a Brownian particle. Or it can be a position of a Brownian particle. Okay. And we can also go and say that these can be also multidimensional. Okay, this set need not be a single dimensional, it can be a multidimensional also. So for example, if I take this continuous variable, I can say Vx, Vy and Vz. This entire set is each of them is a continuous random variable, and the set can be a multidimensional. Okay, so that's what this means. And similarly, if you want to specify the x, y, z coordinates, that is also fine. Now about the probability distribution function. So here this has to satisfy the two conditions. One is that p of x has to be a positive value function, and the second is that p of x dx should be 1. Okay, so here I have written for a one-dimensional continuous variable. Okay, but if it's a multi-dimensional or a discrete variable, you can analogously write. Okay, so we can see that when we try to define a random variable, we define two things: set of possible values, and these values can be discrete or continuous, and these are the examples, or it could be also a multi-dimensional description. And the probability distribution over this set has to be also mentioned, and that it has to be a positive valued function, and then it has to be, when you integrate this over all possible range of the coordinates, that should sum up to 1. Okay, so these are the very basic definition of a random variable. And the way we interpret this is that the function p of x dx, this will give you the probability that the random variable will take the value between x and x plus dx. Okay, so the p of x dx will tell you what is the probability that the random variable will take a numerical value x in the interval x to x plus dx. Again, I am assuming it is a continuous random variable. Now we use this capital X here to denote it is a random variable, okay. And let's say you make another function f of x, okay. So you are making a function of the random variable, we call that as f of x. Now whenever x takes different value, this function value also will be different, okay. Now sometime you are interested in an average description of this function f, okay. So then the average or expectation of this function f of x is basically written as the integral of f of x times p of x dx. So p of x is the distribution function. What we are trying to do is we are actually calculating the value of f of x weighted by different x values that is possible, okay. So this is basically a weightage function here. We also define something called moments. These are expectation values of higher order moments. So we say something like this is called the mth moment of x, okay. So x is a random variable. When I raise this to power m, m is an integer, it can be 0, 1, 2, 3, 4, all that, and then I am denoting this moment as mu m, and we call this as a x mth moment of x. From here, similarly, we define the mth moment as x power m p of x dx. So when you substitute m equal to 1, what do you get? Expectation or average. The first moment is nothing but the average value of x itself, okay. When you put 2, 3, 4 and other numbers, you get basically higher order averages or higher order moments. Sometimes we also use this expectation value in terms of e of x, okay. So this is nothing but the mean, and expectation of x square is the mean square, okay. This is another way of writing the expectations and moments. Or you can generally write the expectation of mth moment as simply like this, okay. So you can see either we use this angular bracket to denote this mean value or this letter e to represent an expectation value, okay. So we can use interchangeably because in some of the books they use this notation, in others they use, okay. So we should be aware of different way of writing this expression. So here for a given random variable, once we know the distribution function, we can get the mean value, and we can also find the variance sigma square. And if you expand this, you will see that this is nothing but so in terms of this notation mu, this becomes mu2 minus mu1 squared. So these are again very standard textbook definitions. So now what we will do next is we will look at some of the well-known random variables like uniformly distributed, exponential distributed, and Gaussian distributed, and then get these quantities. The most simplest form of a random variable is this uniformly distributed random number. Now the interval is between a to b So A is the lower limit and B is the upper limit. Okay, this variable, random variable, can be distributed in this range. So that means I am already giving you a set of possible values. It's a continuous variable starting from A, ending at B. Any value in between, the value can take. Okay, so that is a possible set. Then we have to also give the distribution. So here we say that P of x is 1 by b minus a. So when we say uniformly distributed, what we mean by that is that any value between a and b are equally likely. Okay, one values are not more likely than the other, all are equally likely. Okay, so that's what we mean by uniformly distributed random number. And you can see this probability distribution function is a constant, it doesn't depend on x. Okay, once you specify the range, then it is fixed. So if I plot this function, it would be something like this. So here is a and here is b. Between this range a to b, the probability is 1 and then 0 otherwise. Okay, so this is the, you can see that the probability is equal for all of them. So this value will be 1 by b minus a. So for this particular random variable, let us calculate the mean and the standard deviation, variance and so on. So and then the same approach can be applied for any other random variable we are going to discuss further. Okay, so the first one is to find out what is the mean value. Okay, so our definition is x p of x dx. So for this particular random number, the range is a to b and the p of x is 1 by b minus a. So we take this 1 by b minus a outside because that's a constant, and then we have only x dx in the limit a to b. So we get 2 times b minus a, b square minus a square. Okay, you will get x square by 2, and if you put the limits, you get b square minus a square. 2 comes out here, and this basically becomes simply a plus b by 2. Okay, what it means is, if you have a random number generator, we will see how to generate random numbers. And if you generate a very large number of thousands of random numbers, and you will see it will be distributed in this range, and then the average will be always the midpoint here. Okay, so that's what this means. Now what about the standard deviation? This is a mean value, and we want to look at the variance and standard deviation. So first we get the mean square value. From this formula, we get x square p of x dx. So p of x is 1 by b minus a. We get x square dx, and then we get 1 by 3, so b minus a, b cube minus a cube. So when you integrate, you get x cube by 3. 3 comes out. When you substitute the limits b cube and a cube, you get. Okay, and then if you expand this, you get a square plus b square minus ab by 3. So that is your x square. Sorry, this would be plus, yeah. So the variance sigma square is this. So for the mean square, we get this expression a square plus b square plus ab by 3, and mean value we have obtained here, a plus b by 2, and then we take the square of that. So we get a plus b whole square by 4. So we take LCM here, 12, and 4a square plus 4b square plus 4ab minus 3a square minus 3b square minus 6ab. Okay, so the variance is nothing but b minus a whole squared by 12. And the second example is an exponential distributed random variable. So here we say that p of x is equal to lambda e power minus lambda x, defined in the range 0 to infinity, and lambda is positive. So in one single statement we have defined the range of values, possible values of x. Okay, it can be from 0 to infinity, and the probability distribution function is exponential. What it says is that the smaller x values are more likely to happen than the larger x values. Okay, this is one of the first example of uneven or uniformly distributed random variable. Okay, in the previous case we said that over range a to b all random variables are equally distributed or equally likely, but here we see that we give a weightage. Okay, the smaller x values are more likely to happen than the larger x values in the range 0 to. So range is mentioned and the probability distribution is also mentioned. There will be sometimes a parameter coming into the distribution. So here lambda is a parameter. Okay, and this has to be a positive number. Okay, so now once we define p of x, we can go about and do the same thing like we did here. We can find the mean values. Okay, so mean value will be 1 by lambda, and the variance is 1 by lambda square. So exponentially distributed random variable has a unique feature that the mean and standard deviation are the same. Okay, the standard deviation is square root of this, you will get 1 by sigma, and the mean and standard deviation are the same. Okay, so so this normal or Gaussian random variable is very common in many real situations. Okay, so very large populations, whenever you look at it, you will see any property are very likely to be normally distributed. There is a powerful central limit theorem that also proves that why when many variables are added up, the net effect would be a Gaussian random variable. Okay, and in this case, you can see there are two parameters, one that specifies the mean value, another one that mentions the variance itself. Okay, these are two parameter random variable model, and the range is from -infinity to +infinity. Okay, so if you plot this function, it is centered at mu, and then it's distributed. Okay, and the variance, the width of this distribution is governed by sigma. So these are the two input variables you have to give in. And then if you want to have any higher order moments, you apply the same formula like we discussed before, the moment formula, and then you can get any higher order moments that you like. Okay, so these are some of the very well known and very simple random variables. And so just to sum up, what we did in this class today is that we looked at two scenarios, physical scenarios, where the dynamical outcome seems to be irregular, and that is manifested mainly because the observable quantity is affected by a very large number of independent variables. Okay, Brownian motion, polymer dynamics, and so many other examples. Okay, so the main theme of this course is to understand the dynamics of those processes from a probabilistic point of view or a stochastic point of view. And to begin with, we looked at some very simple discussion on probability theory. How do we define a random variable? What are the properties? What are the quantities we can measure, the means and standard deviation and higher moments? And we also looked at three examples. The uniformly distributed random variable, where the random variable can take any value over a range with equally likelihood. Then two other distributions where we give a weightage. In the exponential distributed random variable, the smaller x values, the small valued functions are more likely than the higher valued numerical functions. In the case of normal distribution, any variable near the mean is more likely to happen. Okay, and these are the low probability values of x that it can take. Okay, and the spread and the mean value are the parameters of the distribution. Okay, so in the next class, I will take a step forward and then discuss what we mean by a stochastic process. So right now in these discussions, I did not bring time. These are all static distributions. It doesn't have any time coding. But like I said before, the polymer dynamics or Brownian dynamics, these are all time evolved problems. Okay, as a function of time, you can measure some quantities. So we'll include time as a variable into the probability distribution function itself. Okay, so that's where we define what is a stochastic process, how time comes into play, or how to integrate time into the probability distribution function itself. Okay, those are the further discussions we'll have in the next class.